Hello and welcome to CPFD's Getting Started with Virtual Reactor 24.1 webinar. My name is Rosemary Clark and I'm the Senior Support Engineer for Barracuda Virtual Reactor, and I'll be your host for today's webinar, and CPFD's Sam Clark will be our presenter. We're excited to have the opportunity to tell you about the new features and enhancements included in our version 24.1 release. This webinar is being recorded, so if you miss anything or you want to share something that you saw with a colleague or a friend, you will be able to do that. The recording will be posted on our website's Webinars and Presentations page under the Resources tab. This webinar should be posted there in the next 48 hours, so make sure you check back then to review the recording. And we would like this webinar to be interactive, and we need your help to make that happen. As you think of questions, please put them in the question panel. We have intentionally allocated a significant amount of time to answer questions after the presentation, so it will help us to stay organized if you put in the questions as you think of them throughout the presentation instead of all at the end. And for those of you who are joining us today who are new to CPFD software, let me briefly introduce our company. Here at CPFD Software, we are advancing multi-phase simulation and technology for fluid particle systems, primarily fluidized bed reactors. Our Barracuda Virtual Reactor software product models the 3D transient hydrodynamics, heat balance, and chemical reactions in industrial units. It is typically used to improve the reliability and performance of these systems through simulation. These are often industrial units that operate 24/7 for quite possibly years on end. For operating units, virtual reactor simulations allow you to look inside the system in a unique way, determine root causes of underperformance, and use virtual testing to reduce the risk of making any changes. And often as you're looking at the software results, other ideas come to mind and additional optimization opportunities are identified. For those of you developing new technology, Barracuda is used to accelerate and broaden that R&D and then quickly commercialize, scale up, and communicate the unique capabilities of your technology to customers, partners, and others. Now let's get to the webinar itself. Our presenter today is Sam Clark. Sam is the Barracuda Virtual Reactor Product Manager and has been at CPFD since 2008. He has worked in a number of areas at CPFD over the years, from software testing to engineering service projects to customer support and training. In his current role as product manager, Sam works closely with CPFD's development team to design features and capabilities for virtual reactor that benefit our customers all over the world. So I'll turn it over to you now, Sam.
Thanks, Rosemary, and thanks to everyone who's joining us for the webinar today. The development team here at CPFD is proud to release Barracuda version 24.1, which has several significant enhancements. If you're a Barracuda user, you should have received our release email earlier this morning. If you didn't get that, please let us know and we'll add you to our email list for release announcements. Version 24.1 is available for download on our support site now, so please log in and check it out. You can find more details about all the things we'll cover today in the release guide chapter of the user manual, along with links to the full documentation sections in the manual. One of the biggest changes users will see in this release is an updated approach for defining cloud resolution. Throughout the Barracuda GUI, the interface for setting cloud resolution has been made more consistent and we hope easier for people to use. An important motivator for implementing this new design is to allow consistent cloud resolution definitions across all ICs, which are initial conditions, and BCs, which are boundary conditions, in an easy to understand manner. Starting in this release, the cloud resolution options, automatic slider bar, clouds per cell, and clouds per kilogram are available at all initial conditions and boundary conditions, and their definitions are the same no matter where they are used. Backwards compatibility has also been maintained, so if you bring in a project from an older version of Barracuda, your setup will not be changed in terms of cloud resolution settings. For new projects created in version 24.1, the default setting for cloud resolution is a slider bar level of medium at the global level. This value corresponds to 125 clouds per cell, which I'll discuss in more detail on the next slide. And additionally, this setting is inherited by all particle species, ICs, and BCs by default. I'll cover this new inheritance capability in more detail as well. The reasoning behind this default approach is twofold. First, the medium slider bar setting works well for typical bubbling fluidized beds that Barracuda users commonly simulate. And second, a clouds per cell basis allows the number of clouds to naturally scale with the grid resolution. If the number of cells in a simulation is doubled, for example, the number of clouds will also double automatically, which is almost always the desired behavior. As I mentioned, the default basis for cloud resolution at all ICs and BCs in version 24.1 is clouds per cell. And it's important to understand how this is defined. The equations and tables shown here are from the user manual, and I encourage you to read these sections of the manual if you want more detailed information. Equation 1.1 is the definition of clouds per cell. It is the number of clouds in a cell of average volume if the particles were at a volume fraction of 1. So even though this condition is not physically possible, it is a convenient and useful way of determining cloud size in the MPPIC approach used by Barracuda. Furthermore, this is the same definition that has been used in previous versions of Barracuda for boundary condition cloud resolution. It had the names feed per average volume and number density manual, but in the hopes of making our terminology more consistent and intuitive, we've retired those older names and they have been replaced with just more simply clouds per cell. A nice benefit of the clouds per cell definition is that we can continue to use the 50 divided by theta p rule of thumb for determining good values of cloud resolution in many cases. This heuristic has been recommended by CPFD for many years when setting cloud resolution for BCs, and it can now also be used for ICs in exactly the same way. The automatic slider bar widget in this release has been updated so that it uses preset clouds per cell values as shown in the table. For many typical bubbling fluidized bed simulations, the average particle volume fraction is often about 0.4, and so the medium setting on the slider bar should work well. For more dilute systems, medium high or high are available, and for very dilute systems, we recommend that you use the 50 divided by theta p rule of thumb and set the clouds per cell value directly instead of using the slider bar. As I mentioned a couple slides back, we do have a new inheritance capability that's been added in this release of Virtual Reactor. This inheritance scheme allows you to easily ensure that cloud resolution is consistent at all ICs and BCs. The default behavior, which I expect should work well in many cases, is for all particle and bubble species to inherit cloud resolution from the global cloud resolution definition. And similarly, all ICs and BCs inherit the cloud resolution setting from the species level. With this default approach, the user only needs to specify a cloud resolution setting once at the global level. And then all ICs and BCs will use that setting, and all clouds in the system will be of similar volume, which is often the desired behavior that you want in your simulation. While the default approach should work well in most of the time, there will be situations where more fine-grained control of cloud resolution is needed. We've designed the inheritance scheme to allow the user to control cloud resolution in very flexible ways. If a particle species needs more resolution, the inheritance can be broken for just that species, and then all ICs and BCs using that species can inherit that resolution. Or, if desired, the inheritance from the species level to the IC-BC level can be broken, and individual ICs and BCs can have their own independent cloud resolution values specified. Our goal was to have a simple default cloud resolution approach while still allowing for detailed control in situations where that's needed. The new options and inheritance behavior have also been applied to BCs using SFF files to control transient feeds. A new checkbox has been added for Use Species Cloud Resolution. For new projects created in version 24.1, this option is selected by default so that the BC will inherit the species cloud resolution setting. For older projects, this option is not enabled by default in order to maintain strict backwards compatibility. When the Use Species Cloud Resolution checkbox is checked, the cloud resolution column will be grayed out and ignored by the solver. Note that if the cloud resolution column is used in the SFF file, the header can be double-clicked and the basis used for cloud resolution can be changed. The default basis is clouds per cell, but you can also choose clouds per kilogram or automatic slider bar levels 1 through 5. Moving on to a few other new features of this release. One is that we've made the directional option the default selection for momentum redirection model. This option was introduced in version 24.0, and we found that it improves the realism of particle movement in many simulations without having any negative side effects. This option influences particle motion in regions near close pack. The directional option causes particles to move in the direction of decreasing stress, as opposed to the previous default of random directionality. We found that Virtual Reactor is able to give better results in terms of angle of repose, as shown on the image in this slide, when this option is selected, and that other aspects of particle motion can also be improved. Moving on to some boundary condition updates, 2 improvements have been made to injection BCs in this release. For those who may not be familiar with these types of boundary conditions, injection BCs allow you to feed fluid, particles, bubbles, and/or tracers at any location within the domain, without the need to attach the BCs to wall faces. They're often used to model gas spargers with many nozzles or perforated plates or other complex feed geometries. In this release, we've separated the particles and tracers into separate tabs so that each can be fed and controlled independently. Additionally, it's now possible to specify a mixture of particles or bubbles species. In previous releases, only a single species could be selected. This new mixture capability follows the same input pattern that you're familiar with from flow BCs, pressure BCs, and other areas of the GUI. And so this should make defining complex feed mixtures a bit more convenient. The other type of boundary condition that we've updated is thermal wall BCs. First, a new heat transfer resistance input has been added to allow more realistic simulation of heat flux through wall surfaces. This allows users to more accurately model heat loss from vessel walls and can also be used for simulations of heat exchangers, heating or cooling tubes, and other heat transfer situations. The specified resistance is an R value that can include effects of conduction and convection resistances. When a non-zero resistance is used, the specified wall temperature is outside the domain. For example, if you were modeling heat loss through the walls of a large FCC regenerator vessel, you would specify the ambient outside temperature. Then you'd specify the R value to account for convective and conductive heat transfer resistance. The Barracuda solver then calculates the heat flux based on the temperature difference between the inside and the outside of the vessel and the specified R value. If a value of 0 is specified for the resistance, the behavior is exactly the same as previous versions of Virtual Reactor. The specified wall temperature is the inside surface temperature of the thermal wall BC, and in this case, no heat transfer resistance is taken into account. The other enhancement to thermal wall BCs for this release is the addition of a direction vector option for selecting the heat transfer faces. This option works the same as the direction vector option you may be familiar with from flow BCs. 3 vector components are specified by the user, and faces that are normal to that vector are selected for the BC. A variation angle can be adjusted to select more or fewer faces, and the option force absolute direction allows you to be even more precise. The example simulation shown here demonstrates both the direction vector feature and the resistance option. The direction vector has been used with the force absolute direction option to only select the bottom face of the angled plate in the middle of the domain. Without the direction vector feature, this face would be very difficult to select without also catching the top surface of the plate and some of the outside walls of the cylinder. The 3 views of fluid temperature correspond to low, medium, and higher values of heat transfer resistance on the thermal wall BC. And in each case, the temperature specified was the same for all 3 of those. The lower the resistance, the more heat is transferred from the hot slanted wall surface to the fluid. Now I'll drop out of PowerPoint and demo a few of the new features in this release. Maybe I will. I'm trying to hit escape. There we go. Okay. So here I have the 24.1 GUI open. This is on Windows, but it'll look the same as what you would see on Linux. The first thing that we'll talk about is the cloud resolution options and where they are located and how the inheritance works. I'm using the gas fire training problem. I'm in the main particles page of the project tree. And you can see we rearranged this a little bit because this added some extra space to have this widget here. But basically you have cloud options and a global cloud resolution slider. So if you know that you want higher resolution for all the clouds in your simulation, you can kick that up. Or if you want to specify the resolution in some different way, like a different number of clouds per cell or specifically some number of clouds per kilogram, you can do that. And then this setting would be inherited to the species level and then to the IC and BC level as well. I'll leave that on automatic medium for now. That's the default, and that's how this project was run. The next level is the species level, right? So when you define a particle species, the default behavior is that this option, use global cloud resolution, is selected. So whatever setting you had in the main particles page, the species will pick that up and it'll pass that information back down to the ICs and the BCs. This is where I mentioned that you can break the inheritance at this point. You can say, okay, I don't want to use global. I want to make this lower for this particular species or higher for this particular species. So you can do that if you desire to have a distinctly different resolution for this particle or bubbles species, depending on what you're modeling. And then the third level would be at your ICs or your BCs. So here, let's take a look at ICs first. You'll see kind of the same widget, right? The cloud resolution group box. And again, the default is give me whatever information the species level has. And again, you can break that here. You can say, okay, for this particular particle IC or bubble IC, I want to do something different. ICs actually do have a few more options than boundary conditions do. So just be aware of that. And these are options that were previously available as well, but now they're under this specify resolution dropdown. So again, clouds per cell, clouds per kilogram, those are consistent with the other levels. For initial conditions, you can also do clouds per region. So if you do that, you can say, okay, I know that I just want 500,000 clouds in the particular region that I'm selecting, and then the solver will just initialize whatever number that you're telling it. So that sometimes that's pretty useful on initial conditions. The other options are what we've called legacy options. So the legacy slider will give you the old behavior of releases before this version. And the definition of the slider levels were a little bit different. It should not be drastically different, but just be aware you'll get a slightly different number of clouds because the algorithm was a little different. Or legacy clouds per cell. And again, that was calculated in a slightly different way, not drastically different, but slightly. So just be aware of that. Most of the time, I'm hoping that just inheriting from the species level is going to be the most convenient and most consistent way of doing this for most cases. Then if we look at boundary conditions, let's look at a pressure BC. In this particular case, we're not feeding particles, but we can still pretend that we will for a moment. So in this case, if you were feeding particles and you wanted to specify that as a mass flow rate, you would edit your feed, and then you would see here this same widget is here. You can use the species level, or you can go automatic, or you can do something specific for this boundary condition. So quite a bit of flexibility there. I'll go ahead and cancel out of there to lose that change. And then for flow BCs, if we go into this one, we can see that this particular flow BC is using a transient file and it's feeding the particles as a mass flow rate. So if we edit our transient file, this is the SFF interface for this. And again, by default, even the SFF is going to use the species cloud resolution. But if you don't want to do that, you can uncheck this box, and then you can see that this column comes to life. and then you can do a different basis if you want to by double clicking on that header. So hopefully that gives users all the tools and the flexibility that they need to control their cloud resolution in a really consistent manner. And when it comes to this, like one thing that you probably want to do, and you may have been doing for a long time, is kind of monitoring what is your cloud resolution as a simulation runs. And so if we go to the run window, I just want to make sure everyone's aware of kind of how to do this. The easiest way is by going to run and clicking monitor run. So I'll click that and TechPlot should pop up here. Hopefully people have been using and enjoying this feature that came out in 24.0. This first page of plots includes a plot that says number of numerical particles, and numerical particles are clouds. And so what we're seeing for this simulation is our particle mass is increasing a little bit because of our feed boundary condition, and our number of clouds is also increasing slightly due to that feed as well. So we're right around 1.1 million. It's not increasing that much. The scale is pretty tight here. And this is one way to monitor what is the number of clouds I have in my system, and is this enough clouds, right? And so generally we tell people that you should probably have like 10 to 20 clouds per cell on average in your system. Right now we're at about 1.1 million clouds, and if we go to our setup grid, we'll see that this simulation has a total of 80,000 clouds. I plugged this into a calculator yesterday. I believe it came to 13 clouds per cell, 14 clouds per cell, something like that. So we're in that 10 to 20 range. So this is not an unreasonably low or unreasonably high number of clouds. And so we're in pretty good shape. We're also not increasing our cloud count really, really fast or decreasing it really, really fast. And so that's what this plot can tell you is for your simulation that you're running, do you have kind of a reasonable global number of clouds per cell? And is that number staying relatively constant, or is it changing in some way that you should be concerned about? So just be aware of that. The other thing that you can do, I'll go ahead and close that. If you look at your visualization data options, there are a few options that can be useful to visualize like what is your cloud resolution doing. There's one on the cell layer, and I didn't select it for this example, but you can do clouds per cell, and this will show you on a cell-by-cell basis how many clouds do you have. The ones that I chose for this simulation were cloud mass and also particles per cloud. So sometimes these are useful for taking a look at what is the cloud resolution, how many real particles are represented by each cloud, how big is each cloud, those sorts of things. So if I go to post run, we'll do a view results, and this should open TechPlot with our typical particle volume fraction view. You'll notice there's not a shortcut over on the side because this is not something that people look at on an everyday basis, but we can double click our contour legend and we can choose, instead of particle volume fraction, this one usually goes to the bottom of the list. If we choose something like cloud mass, this is often a good way to see are most of my clouds kind of similar in terms of the mass of particles that they represent. And with this new scheme of kind of medium slider bar, and then the ICs inheriting that value and the BCs inheriting that value, what you should see in most cases is that the clouds do represent a fairly consistent mass throughout the domain. And that's what we're going for, right? We don't want orders of magnitude difference between particles that are initialized in the bed, for example, and then the same particle species that's being fed at a boundary condition. Usually we want that resolution to kind of stay consistent. And that's what we're seeing here. Everything here is kind of in this greenish blue color, maybe 0.004 to 0.005 kilograms per cloud. So those are a few different ways that you can look at the cloud resolution and just make sure that your simulation is behaving in a good and reasonable manner. Okay, the next thing we can take a look at is some boundary condition updates. As we mentioned, injection BCs have a few things that have been added. If you feed particles at an injection BC, you'll see the particles tab appears. You'll see this same cloud resolution widget that you see at the other boundary conditions. And then one of the new things here is in the past, you had to just select one particle species or one bubble species. But now you have our kind of typical mixture dialog box where you can say, oh, I want 75% of particle species number 1 and 25% of particle species number 2. And those can be fed as a mixture from this injection BC definition. So that's possible now to do a little bit more complex feed than what you may have seen before. And then also tracers are their own independent tab now. These used to be kind of all bundled into one tab, but now the tracers have an independent tab, so you can control those on their own independently from the particles. So that is possible now. The other boundary condition is thermal wall VCs, and so this has a few different options. I'll open up one here. You'll see this new resistance input box has been added. By default, what you'll see is if you create a new thermal wall VC, this will be 0, which is kind of the same behavior as older versions of Barracuda. This means I'm telling you the surface temperature inside the domain if you put a 0 there. But if you put some other value, an R value, then what you're saying is the temperature I'm specifying, like 1300 Kelvin, this is the temperature outside the domain, and then energy has to travel through the wall, and there's this resistance to the heat transfer, either through conduction or convection or a combination of the two, and then the solver will take that into account. The other thing that you'll see is on heat transfer direction. This particular one is still using kind of our old traditional normal surface option, which is fine, right? A lot of times that works well. But if you do want to specify kind of some specific faces that are normal to a vector, now you can do that as well. And so there's this interface has been added, and this is the same as what you may have seen in the past for flow BCs, and it selects the cells in exactly the same way that flow BCs would. So those are the specific GUI changes that I wanted to point out to people. And so let me jump back into the PowerPoint real quick. We have a few more things to show, and then we can get to questions in a little while. So the next thing that I just want to make sure people are aware of is we've recently added a new section to our support site, and this is called application models. A number of people have asked about specific areas of application for Virtual Reactor. So one thing our team has been working on over the past few months is creating example simulations and publishing detailed information about these applications. If you log into the support site, on the dashboard page, you'll see a new button under Training Resources for Barracuda Virtual Reactor Application Models. Click on that to get to the top level page where you'll find our first set of completed models. There are a few on hydrogen production and one on a conditioning tower for the cement industry. Taking the conditioning tower as an example, you'll find that the information is quite detailed, and you can download the Barracuda project for further exploration if you like. We plan to add more application models to this collection as time goes on, and if you have a specific application that you'd like to see us work on, please let us know. We do want to make this as useful as possible for users all over the world, and so we do welcome your input on that. Okay, at this point, I'll hand it back over to Rosemary.
All right, well, thanks, Sam. So we've now covered all the new features in Barracuda version 24.1 that we're going to talk about today. So now is a great time to submit your questions if you have any, and then we'll be answering those questions at the end of the presentation. So be sure to get yours into the question panel now. For those of you that are new to CPFD software, I just want to briefly let you know a few different ways that you can get started working with us. So software licensing is the first method, where your team uses Barracuda directly to set up, run, and post-process simulations. And so we have a number of different licensing options available, so please contact our sales team for specifics. And global teams can take advantage of our global enterprise license option available in most countries. And virtual reactor licenses can be served either on-premise or on the cloud, which opens the door to using both your own hardware and cloud computing resources as well. If you're a Barracuda user who would like to add license tokens to your RLM server in order to run more simulations or take advantage of the speed of multi-GPU, you can contact our sales team. It's easy to add solver, chemistry, and/or GPU tokens at any time to meet your needs. So we also offer engineering services for those of you with a one-off or urgent need, or if you'd like to gain the engineering benefits of modeling your system with Virtual Reactor prior to building out a team to run the software. So contact us if you want to learn more about this option. And the easiest way to get started is with our training classes. Our next class is coming up in December, and we'll have more information about that in a few slides. And training can be combined with project work and licensing in what we call our Quick Start program, which is intended to get you up and running as quickly as possible. We run the first models for you with our engineering services team. Then we hand the models over to you, train you on the software, and provide the software licensing. And this allows you to build out your own in-house capabilities with models that are already up and running. And lastly, we work with people in a variety of custom ways through various R&D partnerships ranging from fluidization research to researching new physics models to technology development. R&D partnerships can be direct with us or collaborative with our strategic partners. So contact us if you're interested in becoming a partner. We have some upcoming events that we would like to highlight. So this week, CPFD is participating in the AICHE annual meeting in San Diego. So if you're there, please connect with us. And next month, CPFD's Peter Blazer is speaking at Altair's ATCX DEM. And join this virtual event on Thursday, November 21st, to hear Peter discuss how Barracuda complements DEM simulation for large-scale thermal and reacting systems. Our final Barracuda Virtual Reactor new user training class of 2024 will be December 9th through 13th. So if you'd like to join this in-depth web-based training course to learn how to use Virtual Reactor, just let us know. You can contact us. PSRI will be conducting their highly respected fluidization seminar in Houston, Texas from January 7th through 10th. And this is a great way to learn about many fundamental topics related to fluidization. And if you haven't had the chance to attend it, we highly recommend it. You can check out our events calendar for more details on these and many other upcoming events. And if you have an upcoming event that you'd like us to put on our calendar, just please send us your information. So now we're ready for questions. So be sure to add your questions in the box if you haven't already. So Sam, are you ready for a question?
Sure.
Okay, so we have one. So when should I not use the default medium slider bar setting for cloud resolution?
Yeah, so I think the main case where the default setting would not work well is for people who are using Barracuda to model fairly dilute systems, right? And so if you're modeling something like a very lightly loaded cyclone or a very lightly loaded riser, then in that sort of case, you would definitely want to use the 50 divided by theta p rule. And if your theta p is like 0.01 or 0.001, then you would need to use a clouds per cell value of 500 or 5,000, depending on your volume fraction that you want to feed into the system. And in that case, the slider bar won't do what you need, but you still have those other tools that are built into the system.
Okay. So we have another question asking any updates to the rotary kiln simulator, and I think maybe that's talking about rotating gravity.
Okay, yeah. So this particular release doesn't have any specific updates to that. I'll drop out of the presentation just to show kind of where this is now. if you want to model a simulation that is rotating about an axis, then that is possible, right? And this was released in 24.0, I think, for this being in the real release as opposed to a beta feature. So instead of using a specified gravity that stays constant all the time, you can specify your gravity direction, and then you can tell Barracuda to rotate gravity about an axis, either X, Y, or Z, at a specific rotation velocity. So this is in the gravity settings. The other thing that we added was even a more general gravity specification where you can vary X, Y, or Z gravity over time. This is more useful for things that are not necessarily rotating, but maybe moving in some prescribed pattern, and the gravity vector is changing there. But yeah, this capability is still the main thing that we have for rotating geometries. The other thing, I've talked to a couple of users who weren't, or who didn't remember that there is a specific script that's included with Barracuda. So if you open a terminal from the GUI, and if you have Python installed in the way that we recommend, I think there's a script, and of course Windows is not completing it for me the way that Linux would. But I think there's a script called rotating gravity animation. And let's see if it'll do that. There we go. Okay, so if you type rotating gravity animation and then a -H, it'll show you the help message. So this is kind of a helper script that connects to TechPlot and rotates the view and outputs the resulting image frames in a convenient way, because otherwise it can be kind of challenging to create an animation from your Barracuda results that show the geometry rotating. So those are the main tools that are available right now for people who want to model this kind of rotating system.
All right, well, thank you. And that's all of the questions that we have for today. So thank you so much for attending the webinar. And if you have any questions, just send us an email at support@cpfd-software.com.
Thank you, everyone. Have a good day.